did you see? Something evil?
Excitement, confusion.
We're going to explore how to find areas using integration techniques, and to do this I'm going to utilise questions 2 and 3 from the preparation task. In question 2 you are asked to integrate between the limits 0 and pi over 4 cos squared x with respect to x, and this value we called I1. Similarly, in question 3 I asked you to integrate sine squared x between the same limits. This was called I2. We also have on the diagram I as the area between the two curves, and this was actually question 1. We have a value for this of 1/2, and what I'd like to do first of all is to explore the implications of the diagram and what we saw in the preparation task. When we are integrating f, for instance, we'll start with f, you're calculating essentially in this case the area under the curve, which I'll shade in now. So all of this I'll shade it in green. So the hatched green area constitutes the area under the curve f, and remember I can represent this as an integral. The integral was I1, so I1 is equal to the integral from 0 to pi over 4 of cos squared x dx, like so. Similarly, we have the area under the curve G. I'll shade this in red. So under the curve G, between the limits 0 and pi over 4, we have the red area. And that can also be represented by the integral I2. This is also with reference to the preparation task. And I2 is the integral from 0 to pi over 4 of sine squared x dx. There we go. What we're also given in the preparation task is an integral that we have to evaluate called I. I was an integral from 0 to pi over 4, but I was cos 2x. And as you know from the diagram in the notes, I is the area between the two curves. This area here, in fact. So I'll just go over this. So the area between the two curves f and g is our area I. And that was, if I just write it down, equal to the integral from 0 to pi over 4 of cos of 2x. And remember that was equal to 1/2. So the area bounded between f and g is 1/2 square units. So what's going on here? Well, we can see from the diagram and from the formula you were asked, or the equation, sorry, you were asked to write down in question 3b of the preparation task, you could see very clearly that I was equal to I1 subtract I2. It was the same value. I1 subtract I2 gave you 1/2, and as you can see here, if I subtract the green, the red area from the green area, that will also give me I, which is worth 1/2. But there's more to it, because if I sub in the integrals, like this. So I'll do it over here, the integral from 0 to pi over 4 of cos of 2x dx. We now know that is equal to the integral from 0 to pi over 4 of cos squared x dx. That's your I1. Subtract the integral from 0 to pi over 4 of sine squared x, which is your I2. But why is this the case? Is this just a coincidence? Does this just happen to equal a half, and so does this? Well, no. Because remember, cos of 2x, we can replace this with an identity. And it was the identity that we didn't actually use in the preparation task. You used the two other identities for cos 2x, but not the one that falls out of the derivation. Now I can rewrite the left-hand side of this as the following. So this is the integral from 0 to pi over 4, and I'll do it in red because this is so important. And just go into the identity now of cos squared x subtract sine squared x. That is absolutely identical to cos 2x. I'll put it in brackets here. I've literally just swapped it out of the integrand. And that's also equal to the stuff we have on the right hand side. So the integral from 0 to pi over 4 of cos squared x dx. Subtract the integral from 0 to pi over 4 of sine squared x dx. Why is this significant? Well, what we have shown is that the integral of the difference of two functions f and g is exactly the same as the difference between the integrals themselves separately. Now, I can generalize this because remember I called the function cos squared x f and sine squared x g. So we can generalize this result now. We'll prove it later, but I can state now that if I have an integral from a to b of f of x subtract g of x, all with respect to x, and I'll just put those in brackets so we can see the distinction. So we're integrating all this together. This is equal to the integral from a to b of f of x dx, subtract the integral from a to b of g of x dx. Okay, and we'll explore this a little bit more shortly. Now we are presented with the definition of the difference between two functions f and g integrated between the limits a and b as equal to the integrals done separately and the difference taken. And we can also see in the diagram that this represents the area bound between the two curves y equals f of x and y equals g of x. Now, in the lead up to this equation, I've stressed the word can in italics. Now, the reason for this is that, yes, the area bound between the two curves can be found using this equation. However, there is a caveat, and this is not always the case. So we will explore a specific case and look at 4 general cases before we go into the formal proof of this definition. So first we're going to look at the function f of x equals 2 defined between x values 0 and 4, and we are going to integrate this between the lower limit x equals 1 and the upper limit x equals 3, like so. And I can also represent this as an integral from 1 to 3 of f of x with respect to x, and you can see quickly working out the area of the square. The area is 4 and the integral value is also 4. Now I have added the function g of x equal to 4 subtract x defined between the same x values, and once again we're going to integrate g between 1 and 3 like so, and the area of this trapezium can also be represented as an integral from 1 to 3 of g of x dx, which also gives a value of 4. By considering the graphs first of all, we have two straight line graphs, and the areas between the two graphs seem to be equivalent. I have a positive area here and a negative area here. When I say negative area, what I really mean is a negative integral, because clearly the total area between the two lines is not 0, it's in fact 1. But because of the positive and negative parts of the integral, they cancel to give a total integral value of 0. We can also see this if we consider the two integrals here and here. If I take the difference between the two of them, I get an answer of 0. We can also look at this in a slightly different way by considering the function f of x subtract g of x, which is equal to x subtract 2. And if we integrate this function between the x values 1 and 3, like so, we can also see that we have a negative integral here and a positive integral here, but a total area of 1 unit. By putting all these ideas together, like so, we can see that if I integrate the difference between the two functions, it is identical as taking the difference between the two functions separately, because they both return a value of 0. But notice that this is not the area bounded between the x-axis and the straight line graph. Nor is it the area bounded between f of x and g of x, because we saw clearly, as we can see here, that the area bounded is 1 unit. Now we will look at 4 more general cases where the area between the two curves is not equal to the integral of the difference between the two curves. Here I want to look at 4 different case studies just to illustrate further, without the need of an example, more generally, why when you integrate between two functions and take the difference in the integrals, it isn't necessarily the area under the graph. If we look at the first instance up here, I've taken f just to be any continuous function, and I've said g is equal to 0, so g is essentially the line y equals 0, or the x-axis. Now if I take an integral between those two curves, well, g is a straight line, but you get the idea. Any integral over a particular closed interval, so let's say a and b, so from there to there, so I'll call that a and call that b, and I want to calculate the integral. Then the integral will indeed give me the area between the two curves, so this one will work fine. Notice that f and g do not intersect at any point. They are completely separate, and f is always greater than g. If we just extend this to a slightly different scenario, where we have f which actually breaks or intersects g is still the line y equals 0. If I calculate the integral between those two curves, so let's take a similar chunk of the x-axis, so let's say from there to there, so there's my a and there's my b. Then the area under the curve will be represented by those two shaded areas. Now if you take the integral, according to this diagram, there is more area beneath the curve, beneath the x-axis than there is above the x-axis. Now this would suggest that I would get a negative overall integral, but as you can see, there is always going to be a net positive area. So here the area and the integral will not be the same, so this won't work. In the third case, we have two functions f and g. Now g is now a continuous function in a similar vein to f. F is always greater than g, and if I take the integral between the two curves, so from 2 points A and B, so we'll do it like that. So x is A and x is B. The integral between the two curves, so the integral of f subtract the integral of g, will give me that area there, which is exactly the same value as the integral, which is exactly the same value as the area. No problems. Now if I do the same thing here, we have f and g which seem to swap places. There is an intersection. So here I have, let's say I do an integral from A to B between the two curves, like so. Now this time we're doing f subtract g, of course, from the definition. F subtract g, f of x subtract g of x. On the left hand side before the intersection, f is clearly above g, so that will give me a positive area or a positive integral. On the right hand side of the intersection, g is now above f. So if I have f subtract g, the area I will get will be positive, but if I have g subtract f, the area, or I keep saying area, the integral I will get will be negative. But clearly there is an area we can talk about. You cannot have a negative area. So this means that when we have a situation like this, the area and the integral will not be equal. They can't be, because we have functions swapping places. So the area and the integral will not be the same here. So what do all these case studies have in common, or what stands out? Well, if you notice, as long as f is greater than g, then the integral will be equal to the area where there's no intersection. If f and g intersect at any point, the area and the integral will not be the same. So this is an important distinction we need to remember. Now we're going to look at the proof of this key property of integration. To do this, we're actually going to look at the definition from first principles of a derivative and then move on to integration in part 2. In part 1 of the proof, we are going to hopefully try to prove that the derivative of the difference between the two functions is identical to the difference of the derivatives. So f-x subtract g-x. I've put the definition of the derivative here because we're going to be using it, and I've highlighted the substitutions because that's going to be a key focus when we're writing out the steps. Let's get to it. So on the right hand side, on the left hand side I should say, we're differentiating f of x subtract g of x. This is our entire function. So when we use the definition, I have to replace my f with f of x subtract g of x. And what I mean is this. So I'm going to substitute it in now, and this is what we're going to get. So it's the limit as h approaches 0. Okay, and I'm going to do the x plus h part first. Remember, the h is the infinitesimally small increase in the x value, and then we take the limit as it tends to 0. Now I'm subbing x plus h into all of this. Let's do it. So it's going to be f of x plus h. Okay, that's for the first bit. Subtract g of x plus h. I'm just going to pause there. Now we have to subtract f of x itself now from the definition. Now f of x in this case is f of x subtract g of x. So I've got to subtract this function from this expression here. There we go. Now, we can see, hopefully, that there is the definition of the derivative of f and the derivative of g lurking in here somewhere. Let's collect the f terms and the g terms together. So this is the limit as h approaches 0 of f of x plus h subtract f of x. So that's collecting these two terms together. I'm going to subtract. I'm going to open a bracket again. So I'm going to subtract, open a bracket, g of x plus h subtract g of x, and then we'll close the bracket. And just check, just convince yourself that that is actually the same as the step before. I've just collected the g of x plus h and the g of x together and subtracted them inside the bracket. All of this again is over h. Now clearly we have the definition of two derivatives, and because limits are linear operators as well, we can take the limit of any term in this expression. Now it will only affect the terms with h in them, but if I'm able to do that, I can set up the f derivative and the g derivative. Right, now we have the difference between two derivatives. This is simply the derivative of f subtract the derivative of g, and we're done. Next, by stating f of x as the antiderivative of f dash x, and similarly with g of x as the antiderivative of g dash x, we can apply this result to integrals and complete the proof. Next step in this process, I've defined two antiderivatives. An antiderivative is exactly what it means. It's the function that is the integral of whatever the integrand is. So in this case, the antiderivative of f dash x is of course f of x. And you can write them like this as integrals. Here we have the antiderivative g of x of g dash x. And we also discovered when we differentiated f of x subtract g of x as a single function that we got the difference of the derivatives. What I'd like to do now is to integrate both sides of this equation, and hopefully we'll bring the antiderivatives into play. Let's do that now. So if I integrate, so integral sign at the front, a dx, integrating with respect to x of course, all of that on the left must be equal to the integral of everything on the right hand side. And just so we're clear, I think we should put the integrand on the right hand side in brackets because we have two terms there. That's going to be f of x subtract g of x. Great. The next step, on the left hand side, notice we are integrating a derivative. These are effectively inverse operations. The integral of a derivative just returns the function back. So the left hand side is very simple. I think we saw this when we did integration by parts. So on the left hand side, you're going to get f of x subtract g of x. Very simple. On the right hand side, there's nothing really more we can say about this. We are just integrating the difference between two functions. I'm going to leave that as it is. So this is going to be the integral of f dash x, the derivative of f of x of course, subtract g dash x with respect to x. But notice what we can do with the left hand side. We stated, or I stated at the beginning, that we have two antiderivatives. We know that f of x, which is here, can be represented as the integral of f dash x, and similarly with g of x. So I can now replace the f of x here and the g of x with these integrals. So let's do that. So we have on the left hand side the integral of f dash x dx subtract the integral of g dash x dx, and all of this must be equal to the right hand side again, the integral of f dash x subtract g dash x dx. And I've got to close that bracket there. Now there's our result. So it's written the opposite way around, but we can see that if I want to integrate the difference between these two functions here, I get the integrals written separately.
You have survived, barely, but you must now do the word examples.
Our first worked example is to find the bounded area R between the curves y equals f of x and y equals g of x. F of x is equal to cos x multiplied by the square root of 1 plus sin x, and g of x is equal to cos squared x. Both curves have domain between 0 and pi over 2 inclusive. You may recognise these two functions from the preparation task. So with the integration done, our main focus will be on the reasoning behind finding the bounded region R. This example draws again from work you did in the preparation tasks. You're given two functions, f and g. F of x, cos x multiplied by the square root of 1 plus sin x. This was question 4 in the preparation task. You were asked to integrate this with respect to x, and I've just jotted down the result here for reference, and I put a plus c in there as well. We're going to be carrying out a definite integral, so that won't be necessary, but just to make this precise I've put it in. Similarly, we have g of x, which was cos squared, and when you integrate this function you get this expression here. Again, if you haven't done question 2 from the preparation task, just have a go at integrating cos squared x with respect to x. You'll need to use one of the double angle identities. In this example then, we have to calculate an area bounded between f and g. I'm just going to sketch what was given to you in the diagram. You're given a diagram which essentially looks like this. So you've got a y-axis there, an x-axis, I'll just label those as well. There's the origin, there's y, and the curve f, which is cos x multiplied by the square root of 1 plus sin x, comes over like so, and cos squared which is all positive, of course, behaves like this. Now let's just illustrate what we're being asked to do here. We want to calculate the area bounded between the two curves, which is called R. This value here, where the curves both intersect the x-axis, is pi over 2. Now this means that when I integrate f of x between the limits 0 and pi over 2, that will give me the area under the curve f. Now the curve f, remember, was the first curve I drew, and it's going to be all this area here. So that area is represented by this integral. So it's the integral from 0 to pi over 2 of cos x multiplied by the square root of 1 plus sine x dx. So that's the first integral. The second integral is going to be the integral of g between the limits 0 and pi over 2. Again, if I do that, this will return this area here. Okay, and that looks rather a lot like my shirt, doesn't it? And this area is going to be represented by this integral. So it's the integral from 0 to pi over 2 of cos squared x dx. Now then, we're going to apply our result from the proof that was stated earlier. We can clearly find the area bounded between the two curves, so that would be this area here, which I'll just put dots in. That area, because this is the area R that I wish to find, and it's the difference between the two integrals. Okay, so it's f subtract g. Now I can do this by setting up the following definite integral. So R is going to equal the integral from 0 to pi over 2 of cos x multiplied by the square root of 1 plus sine x subtract cos squared x. Okay, all with respect to x. Once this is evaluated, this will give me the area that I want. So now we can apply the results that we found in the preparation task and evaluate this definite integral. So this is going to equal, let's open a big square bracket because the integration has been done. Now for the first integral, if you remember from the previous video, the integral of that, well, let's write it in. It was 2/3 of 1 plus sine x to the power 3 over 2. And remember, I put a plus c in the previous video. We can dispense with that because definite integrals will make the constant cancel, so you don't need to put those in. And the second integral, which is cos squared, which is here, the result was, if I integrate that, I get 1/2 of x plus 1/4 sine of 2x. And we are subtracting both of these. So I'll put a negative sign there, and then this is being subtracted from the first, and all of this is being integrated between, or it has been integrated, but it's being evaluated between pi over 2 and 0. So upper limit and lower limit. Let's substitute in the values. We're going to need a lot of room here. So this is going to equal big square bracket, and let's substitute in the upper limit. Well, that's going to be 2/3 or 1 plus sine, and if I substitute in the upper limits, I'll do that in red. So that's pi over 2 like so. Close the small bracket there, to the power 3 over 2. So I've substituted pi over 2 into this expression here. Remember, of course, I'm subtracting 1/2 multiplied by pi over 2. Close that. Plus 1/4 sine of 2 lots of pi over 2. Now I'll just multiply that straight away. 2 lots of pi over 2 is of course pi, like so. Close that bracket. Okay, and then there's another bracket to close. So this is the upper limit. Okay, with pi over 2 substituted in. We'll evaluate that in a minute. Now on the second line, because this is a long calculation, I'm going to subtract the lower limit all substituted in. So this is going to be subtract. Now let's open a curved bracket. So that's going to be 2/3 of 1 plus sine of 0 this time. And then I'm subtracting 1/2. I'm putting this in. I know this is going to be 0, but just for exactitude, I think it's worth putting in so you can see the steps. 0, and then plus 1/4 sine of 0, just to finish that off. Zero. And then just a case of closing all the brackets now. So close that bracket for that one. I've got 3 brackets to close, and then the big square bracket as well. Right, let's see if we can argue away some of this. Well, sine of pi over 2, as you all know, or you should know, is 1. So I know that's equal to 1. And I get to use my blue pen for a change. That's equal to 1. This is going to be relatively straightforward to evaluate. Half pi over 2, we can work that out. Now sine of pi is of course 0, so that's going to equal 0. Nothing to worry about there. Sine of 0 of course is 0. And this is of course half of 0 is 0. And this is equal to 0. So not much going on in the lower limit, but plenty going on in the upper limit. So let's just simplify this. So this is going to equal. Now let's just, I'm going to put the upper limit again in brackets just to make it distinct. We're going to have 1 plus 1 to the power 3 over 2. So that's 2/3 of 2 to the power 3 over 2. Okay, so that's for the first product there. Then we're going to subtract 1/2 of pi over 2, which is pi over 4. And then 1/4 sine pi, but we've already said that's 0. So that's all that's left of my upper limit. Okay, and then I'm subtracting whatever's left in the lower limit. Now I'm going to have 2/3 multiplying 1 plus 0, so 1 to the power 3 over 2 is of course 1. Multiply that by 2/3, so I'm just going to be left with 2/3. And in the second part, zeros everywhere. So that's just going to be subtract 0. So to conclude, I'm going to have 2/3 multiplying 2 to the power 3 over 2. What I think I'm going to do is I'm going to factor out 2/3 from this. So this is going to give me 2/3 multiplied by 2 to the power 3 over 2, subtract 1, and then all I'm going to be left with is subtract pi over 4. Like that. Now, you're asked to give the answer to 3 significant figures. If you evaluate that on your calculator, so your calculator returns an answer of, if you just try that, of 0.4335. So 0.4335, etc. And to 3 significant figures, of course, so this is approximately equal to 0.434. So this is square units, of course. In example 2, we are again asked to find the area bounded by the curve y equals h of x and the x-axis. There are 3 points of intersection with the x-axis at the origin and the points A and B. The function h of x is x multiplied by cosine of pi x, and the domain is all real numbers greater than or equal to 0. This example, we do need to apply what we have learned in the previous example and in the proof. What I've done is I've sketched out the diagram you've been given, and you're given 3 points of intersection, the first being the origin, and then 2 other points, A and B, in the positive x direction. The function h of x is x cos of pi x. Now we're asked to find the area of the shaded region. This is a prime candidate for recognizing that integration and area do not necessarily coincide. If we look at the first part of the integral between 0 and a, I'll just shade that in. This is going to be a positive value because the curve is above the x-axis. The second part of the curve between a and b lies below the x-axis. If I shade this in, we're going to see very quickly, or you'll know already, that this is going to be a negative value when we integrate between a and b this function h of x. So the naive approach would be, well, if I'm going to find the area, surely I just integrate from the origin up to b, and hey presto, I get my area. But now we know that this can't be done because we have an intersection between the x-axis and the curve. So this integral needs to be done in 2 stages. We need to integrate between the origin and a, and then between a and b separately, and then combine our answers. So the first task is to find out what are these points a and b so we can sub them in. Okay, so let's write down our function, and we have an equation to solve. So we have x cos of pi x, and we would like to know, in order to get these values for a and b, o is obviously of course the origin, so that would be 0. We need to find the roots, so we need to set this equal to 0 and solve the equation like that. Now we have the product of 2 values essentially. We have the product of x first of all, and cos of pi x secondly. Now when we have a product of 2 numbers, the solutions have 2 possibilities. We have either x is 0 or cos of pi x equals 0. So let's write that down. So either x equals 0 or cos of pi x equals 0. Clearly, this is the origin. This is where the O-intercept is. The second one, cos of pi x equals 0, we need to extract two solutions from this. Because this is a trig equation, there is an infinite number of solutions. We need two to find out the points A and B. So what I'm going to do next, I'm going to solve this as a trig equation. So I'm going to set up a principal angle. So we're going to work on this now. And I'm going to do this up in the corner. So we're going to say let big X equal pi x. All right. There we can find our principal angle. So therefore, cos of big X must equal 0. So x is the inverse cosine of 0. Now what this means is that this is going to be my principal angle. So if you do that, you're going to get pi over 2, 90 degrees in old money. So this is your x. All right. Now on a cast diagram, or if you want to sketch the graph, that's absolutely fine. This is really nice because you're going to have two quadrants where we apply pi over 2. Now, it doesn't actually matter which quadrant you put this in, because you'll see very quickly that you're going to get the same value. So, because cos x equals 0, this value is neither positive nor negative, and this means that you can put this angle pi over 2 into any of these. But I'm going to just for the sake of argument, I'll just say, let's assume 0 is a positive value. I mean, we know it's not, but it doesn't really matter. You'll see in a second. And then when I put my angle pi over 2 in the two quadrants where C is positive, so here and here, so I put pi over 2 in, you'll notice that it would have the same effect as if I'd have put pi over 2 into the T or S quadrant. So this is going to return two angles. So now I can solve my equation. So we're going to have a situation where x is pi over 2, that's my first solution, or x is going to be 3 pi over 2, which is my second solution. Because remember, we go round anti-clockwise, don't we? So like that. That's the positive direction. So let's write down what our solutions are. So big X is going to equal pi over 2, that was our principal angle, or 3 pi over 2. Subbing pi x back in now, we now have this. So therefore, pi x equals pi over 2, or 3 pi over 2. And I'm just going to do an implies now. So we've got our answer. So dividing through by pi, we're going to have x is going to equal a half, or 3 over 2. Great. Now we have the x coordinates of a and b, and we can set up our integral. Next, I've added our solutions to the diagram. So we have points of intersection. Remember, of course, that x is defined only for positive values and 0. So we have an intersection at 0, at x equals a half, and x equals 3 over 2. These were the solutions we've just found, and I've just written the coordinates of the origin, of course, and a and b. Right, so now we're ready to do the integral. We're going to do this in two parts. So the first part, the green part, the positive part, is integrating from 0 to 1/2, and we're integrating the function h of x. Now, because we're going to use the same antiderivative, so whatever the integral of this is, we're going to use it twice. It would be a good idea just to first of all find out what the integral of this is as an expression, and then sub the limits in two cases later. So let's do that. So the first thing I'm going to do and I'll write this down as an instruction. So first, we're going to find the integral with no limits of x cos of pi x dx. We'll apply the limits later. How are we going to do this? Well, we have a transcendental function cos of pi x and a power of x. This is a prime integration by parts candidate. Let's write down what our u's and v's and their derivatives are going to be. U equals x, and dv by dx, which is the second term in the integrand, equals cos of pi x. And remember, of course, you choose your u to be the power of x unless there is a natural log in your integrand. Now let's write down what we don't yet know, and that's the derivative of u and the integral of v. So the derivative of u is easy. It's just going to be 1. Let's write that in. So du by dx equals 1. And this is a standard result for v. Remember, if you integrate cosine, you get sine, and because there is a constant inside the cosine function, that gets extracted out and reciprocated. So it's going to be 1 over pi. Remember, pi is just a number, a constant. Sine of pi x. Close the bracket. So we have all the ingredients now. Let's partition this and carry out the integration. So this is going to equal uv. So that's going to be x. Well, I'll put the 1 over pi first. So 1 over pi x sine pi x and then I'm going to subtract the integral of v du by dx. So that's going to be the integral du by dx is 1. So it's just going to be 1 over pi sine of pi x. I've just run out of room, haven't I? I'll put my dx there, like that. Okay, let's keep going. So we have nothing much we can do with the first term here. I can bring the 1 over pi out to the front. Let's do that. So this is going to be 1 over pi x sine of pi x, subtract 1 over pi, and then I'm just going to focus on the integral of sine of pi x dx. And this time it fits just about. Okay, so the integral of sine of pi x. Standard result again in a similar way to this. The pi is extracted out and reciprocated, and if you integrate sine, that's going to be negative cosine. So let's write down our answer now. So all this is going to equal 1 over pi x sine of pi x. Now then, because this is negative, this whole second term is going to become positive because I have a double negative here. In fact, let me just write in that step so it's really clear. So this is going to be subtract 1 over pi, and I'm going to put the integration of this inside a bracket. I just want you to see it clearly. So that's going to be negative 1 over pi cos of pi x. Okay, and we'll close the brackets as well. There is a plus c, of course, but because we're using a definite integral, we don't need to use that. We don't need to include it. And finally, so this is all going to be 1 over pi x sine of pi x plus, now we've got 1 over pi times 1 over pi, both negative, so it's plus, and then pi squared in the denominator. 1 over pi squared cos of pi x. Okay, and you can put a plus c if you want. Okay. Now we're ready to evaluate these integrals. So the green part, I'm going to call this area R1. All right, so I'm just going to so this is R1 here. In fact, let me do it in green. R1. And we're integrating our function between 0 and a 1/2. Now we've done the integral, so it's just a case of subbing in the limits. So we have to be careful here. This is going to be a little bit technical. So R1, and it's positive, so I don't have to worry about the sign of my answer. I'm going to get a positive answer for this. So R1 is going to be, now remember it's been integrated, but I'll just write it in. So it's the integral from 0 to 1/2 of h of x dx, like that. And this is simply our result previously, which was 1 over pi x sine of pi x plus 1 over pi squared cos of pi x. We will dispense with the plus c, and this is evaluated between, I'm going to do my upper limit in red and my lower limit in green so we can see it clearly. So that's going to be 1/2 and lower limit of 0. Let's do this. So I'm going to drag this across so we have a bit more space. So this is going to equal, now we'll substitute in the upper limit, so curve brackets now, 1 over pi multiplied by 0, beg your pardon, 1/2, like that. I can't do the black pen, red pen switch, not there yet. And then sine of pi x, so sine of pi times x, now it's going to be pi over 2. So you see how the pi is going to come to our rescue. It's going to simplify our answer quite a bit. That's pi over 2. Close that. And we're going to add the cosine part, so plus 1 over pi squared. Cosine, and again pi times 1/2, so that's pi over 2. Close the bracket. That's the upper limit done. All right, so I'm going to close my outer curve brackets. Now we're going to subtract the lower limit. So I probably won't have enough room here, so I'm going to just do this below. So this is going to be subtracting 1 over pi multiplied by, now there's going to be a lot of cancellation here, so we've got 0. The important thing though to remember is don't get carried away. If you're subbing in 0, don't assume everything's going to cancel, especially when cosine's involved. So 0, close that bracket, and then sine of 0 like that. And then we've got plus 1 over pi squared. And cos of 0 again. And that's the bit you've got to be careful of. And close the upper limit, sorry, the lower limit bracket. Okay, let's see what we can do here. Have we got anything that's just going to cancel? Well, I alluded to that earlier. Sine of pi over 2, well, that's 1, so that's not going anywhere, but it will simplify. Cosine of pi over 2, however, will be 0, so that's going to go. This term here is going to go completely because we're multiplying by 0 within the term, and cos of 0 of course is 1. So we can put all this together now and hopefully get our value. So all this is going to equal, so we're going to multiply 1 over pi multiplied by 1 over 2 multiplied by 1, so that's 1 over 2 pi. Let's write that in. So 1 over 2 pi. This is nothing, so that's my upper limit finished. And then my lower limit, 0 there, and then I've got 1 over pi squared multiplying by 1, and that's being subtracted, of course. So that's going to be subtract 1 over pi squared. So this is the exact answer. So for R1, so that's the area of R1 finished. Next up, we're going to look at finding the area R2. Now, what I've done so far is I've expressed the integral of hx. Now, I put in the limits from 1/2 to 3 over 2. These are our points of intersection A and B here, so I've done that already. We've evaluated the integral as an expression in terms of x. We did that earlier, so I'll put that in. And then we have the limits 1/2 and 3 over 2 here. So the upper limit is in red and the lower limit is in green. Now I've left an equal sign hanging over here for the time being. We need to be clear about what we're evaluating. So if I integrate this curve between 1/2 and 3 over 2, ask yourself the question, is the sign going to be positive or negative? Okay, and clearly, because this is below the x-axis, this is going to give us a negative answer. But because we are finding the area of R2, we need to make this distinction in what we're trying to express here, because if I'm finding the area R2, then, and I know that this integral is going to be negative, then I have to compensate for that by writing negative R2, as in negative area, is equal to this integral. So I'm going to put that in. So this is going to be negative, my pen right, so negative R2, like that. Okay, so we've made that distinction. Now all we have to do now is evaluate the integral. Let's get started. So curve brackets, upper limit, subtract the lower limit. We'll need a bit more space, so let's just move over to the left a little bit. So that's going to be now 1 over pi multiplied by x. Now x, remember, is 3 over 2, so I'll put that in. Like so. Then we're doing sine of pi x, so this is going to be the sine of pi multiplied by 3 over 2. So in other words, 3 pi over 2, that's going to go in here. Like that. And then I'm adding 1 over pi squared cos of the same angle. So cos of 3 pi over 2. like that. And that gives us our upper limit, okay? So we evaluate that and we have the upper limit. I'll just close the brackets now. So 3 pi over 2, close that, close that. Right, so that's the upper limit. Now, just for space, I'm going to put the lower limit underneath. So we're going to be subtracting the exact same expression, but I'm going to be subbing in 1/2 instead. So it's going to be 1 over pi multiplied by 1/2 this time. And close that. Then we've got sine of 1/2 times pi, so that's pi over 2, which we know is 90 degrees, of course. So you might be already evaluating these in your head, just to get a little bit ahead of yourself there. So let's close that. And then we're going to add 1 over pi squared multiplied by the cosine of, again, pi over 2. And we close the brackets. And then we're going to see what we've got. So there's going to be quite a bit of cancellation here. And remember that this lower limit, we actually evaluated it as the upper limit for R1, which we wrote down. So I know all of this is going to give us 1 over 2 pi. So all I really need to worry about is what's going on in the upper limit. So let's have a look. Well, 1 over pi multiplied by 3 over 2, that's obviously a value. If I take the sine of 3 pi over 2, that's the sine of 270, which is -1. So I'm just going to make a note of that. So this bit is equal to -1. And then I have the cosine of the same angle. So cosine of 3 pi over 2, that's going to be 0. And all the rest of it we actually know. So we can evaluate this just to the right over here. So let's do that. So this is going to equal so carrying on from before, 3 over 2 pi and because of the -1, that's going to be negative. And because of the lower limit, we know that's 1 over 2 pi, so subtract 1 over 2 pi, like so. And if we just collect those two terms together, that's going to give us -4 over 2 pi, which is basically going to give us -2 over pi. And there we have our integral evaluated. Lastly, let's put all our ideas together and we'll evaluate the total area bounded between the curve and the x-axis. I've just written down the result we've just evaluated. Remember, that was -R2, the integral from 1/2 to 3 over 2, and we got -2 over pi. This means, of course, that the area R2 is the positive version of this. So I'll just put a little implies there, just to explain that we've acknowledged that. So this implies that R2, of course, is 2 over pi. Like so. We've had a R1 written here for a while. So to get the total area, we're going to add R1 and R2 together. So our overall area was R. So R is equal to R1 plus R2, both positive, which is equal to 1 over 2 pi, subtract 1 over pi squared, plus 2 over pi. Now, we do have some like terms we can collect here. The 2 over pi and the 1 over 2 pi, they are amounts of 1 over pi. So we have a half of 1 over pi plus 2 of 1 over pi. So essentially we have 2.5 1 over pi. I'm going to write that as an improper fraction. So our final conclusion is going to be this, or our final answer. We're going to have 5 over 2 pi subtract 1 over pi squared. And there's our final answer.